And so there are a lot of names on the next slide. So there's a title slide. It's important to say this is part of the UK's exascale software initiative, Excalibur, and we have a cross-cutting initiative to do things which are useful, we hope, to multiple science activities. Loads of names. There's some DDN names and there's some stack HPC names, and they've been doing them make these things work in the storage layer. And my group and the National Centre for Atmospheric Science have been doing work in the application layer. So why am I here? Because co-design is not just about software and supercomputers, it's about hardware and analysing the products of supercomputers. And I think there's an opportunity actually for Lustre in this space, so I wanted to talk to you a little bit about that. So to give you some context for why I'm a climate scientist talking to you, a group of storage people, in fact, why I've spent my entire career worrying about storage and HPC instead of the climate science that I'd like to do, is because we have a problem. So a little bit about the problem. So we're trying to simulate the climate. So we have representations of the land, of the atmosphere, the sea. I can tell that you can't read these things, but there are lots of words in these boxes: infiltration, runoff, nutrient loading, all the things that you might expect to worry about if you're worrying about the Earth system and how it might change with anthropogenic carbon. And we do this with models which represent the world in grid boxes, and we have lots of grid boxes. So state-of-the-art models now have more than 1,000 by 1,000 X and Y and 100 in the vertical, so you've got 10 to the 8 numbers already. And then what we do with these models is we basically have the state of the atmosphere at a particular, well, of all the system, the atmosphere, the ocean, all the rest of it, at a particular moment in time, and we iterate forward and work out what the rate of change at that moment is, and then work out the state in the future. So we take our 10 to the 8 numbers. Actually, it's 10 to the 8 for one field, so if temperature, well, we've got a few other fields. In fact, we have another 100 fields, so roughly. So now 10 to the 10 numbers, and we move them forward one after another. And we have to know about the state of those numbers after some time to write them out to do some analysis. So 10 to the 10 numbers, multiply by a number of bytes, and you start to see why this is a big problem. And over the years, the problem's been getting bigger. Back in 2000, we used to represent the world with boxes that looked like the ones on the left. That's the UK as it was in 2000, believe it or not. Over the years, we've got better. So down here, you can see what the same domain looked like in a what we called a N1024, roughly a 12-kilometre boxes around the world. But the whole globe's like this. I'm just showing you a piece, because if I showed you this on a big screen, you wouldn't actually be able to see the pixelation, whereas you can just about see the pixelation. And we're trying to go that's 12 kilometres. The state of the art now is to try and head towards 1 kilometre. And why do we care about all that resolution? You can kind of see in these plots here of some extratropical cyclones as seen in a 130-kilometre model and a 25-kilometre model. And this is impacting on the UK. The colours are, what are the colours? The colours are sea level pressure. I beg your pardon, the isobars are sea level pressure and the colours are wind speed, and this is precipitation. And you can see the difference between 130 kilometres representation of the same storm and a 25-kilometre representation. You get much more intense rainfall, much more intense wind. So if you want to know what's going to happen in the future in terms of extremes, we have to go to high resolution. And that's really the exascale problem. This horribly complicated graph is trying to get across the fact that we like to run lots of different simulations, many different versions of the same simulation to know what's going on, to understand uncertainty. We want to push in resolution down from 100 kilometres, 25 kilometres, down to 1 kilometre, because as we push in resolution, we start to resolve the things that matter for understanding what's going on in the world. But in terms of doing that, the state-of-the-art computing, we're kind of sitting on this line here with Archer 2. This is Lumi, the Euro HPC platform. This is where you'd be on Frontier or Fugacal. Basically, pushing in this direction is the exascale problem. And as you go up there, you're coming down to silly numbers per field. So if I was showing you those maps of temperature or whatever, we're now looking at 500 terabytes to represent one field at 1 kilometre. And we've got lots of fields and we've got lots of time steps. So we clearly can't do that. We have to do things like compression and all the rest of it. And that's really where we're at. And other areas of science have the same problem. Yeah. Okay, so what are we going to do to try and at least manipulate our workflow problem? However, we've decided to store these numbers. How do we then use the numbers? So we create them, but we need to use them. And often they're not in the same place. I already mentioned Lumi, so people run codes on Lumi, we run on Archer 2. If I want to difference the two simulations, I'm moving a lot of numbers. I don't really want to do that. Moving numbers, even on a local area network, is an expensive proposition, expensive in time or CPU cycles or whatever. So the question is, can I avoid some of that movement? As you, I think, all know, all storage systems have rather a lot of compute in it nowadays. The Jasmine system that I used to be responsible for had a 40 petabyte storage piece of storage with Quobyte, which was the software running the storage, and sitting on 131 compute nodes, which are doing a bit of error correction and shuffling the bits and bytes around, but are actually not really doing very much. So the question is, can we use the compute that sits inside storage? And some modern storage is using GPUs to do error correction or whatever. So there's quite a lot of compute available if we could just work out how. And over the years, people have been talking about computational storage and talked about throwing containers or virtual machines or functions into the storage. But I'm about to show you that that's not as easy as it sounds, and brings all sorts of security problems. So this is probably not very readable for those of you at the back. Let me turn around and just read that last sentence. So what we're going to do is decide that if we limit ourselves to just doing reductions in storage, so calculations that reduce the number of numbers that have to come back from storage, like means or counts or max and min, a big part of an analysis workflow is doing that stuff. And of course, that's exactly what we put in MPI on HPC for much the same reason. So can we utilize that in storage, and how can we do that without making trouble for the application? And the answer to that is we can use workflow tools that can be aware of what the storage does. And then the user application doesn't really need to know at all whether you've got computational storage. So the workflow tool that we've built this system around is Dask, which is a Python tool. The take-home message from this slide is Dask, before it does any calculations, works out a scheduler graph of what all the tasks are in the calculation, and then assigns those tasks to compute units. But of course, if it's worked out what you're going to do, part of what it's working out is what you're going to read from storage and what you might be reading from storage just to do a reduction. So what we've done is say, can we manipulate the task graph to push the tasks into storage? And the answer is yes. But the hard part of doing this is storage is a little bit complicated. You all know that. But if you just think about if I'm trying to store one of these grids of the world in there, I might have a bunch of boxes for my X, Y. In this case, I've forgotten Z. But if I just think about X, Y, and T, each time step is going that way and my spatial's going. If I want to just deal with that map there, all depends on how I've written the data to storage. If I've written the data that way, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, then I'm doing another thing while I'm doing that. I'm actually going to write this in chunks. So I'm going to write the first 6 numbers there, and because I've already said we've got too many numbers, we compress those numbers before we write them to storage. So if I then write the next 7, 8, 9, 10, 11, 12 and compress that lot, write them to storage, to get that map, I have to bring both chunks back and decompress. So I've gone through that. That's not what's supposed to happen. That's what happens when you press the wrong button. Okay, now, incidentally, I've got a lot of words on these slides. That's for people for later. I'm going to talk you through. You don't have to read the words, I hope. You just look at the pictures. So what about if we chunked it differently? If we wrote this block of data and then this block of data, then clearly, if I was after the same option, then in this case, I just need to read and write one chunk to get that map back. And it turns out that if you do the maths, it's far more optimal, if you don't know what way you're going to read the data, to write chunk data like this rather than chunk data like that, because it's optimal no matter which way you come in. Yes, there's a direction that's worse than it would be if I did this, but all other directions are better. So chunking is a really important part of what we do, and we compress by chunk. But if I'm doing computations in storage, I've got to handle all that before I even get to the computations. And I just gave you an example of getting a map. Now I want to do the computations. So if you think about what you're doing with a graph of what's going on, essentially if you want to do this kind of calculation over a bunch of chunks, if you want to take the mean, you're taking the mean of a bigger area across chunks, then for each chunk you take the mean, and then you take the mean of the means, and then you get your final mean. And this is what Dask does. Dask's designed to say, oh, I've got lots of different computational units. I'll break everything up into computational chunks, and then I'll do the computation on each computational chunk, and each computational chunk will deal with lots of storage chunks, right? Dask's handling all of the thinking around reading all the storage chunks and the computational chunks. So that's why we can do this, because Dask's doing all the heavy lifting. We just need to get right down the bottom and say, where do you read the storage chunks? And if you do that, we'll just talk through this one a bit slower. So what's going on is essentially what normally happens is you allocate arrays to computational chunks. You send some index information to each process. Each process reads some chunks, does the means, aggregates the partial means, and finishes. That's just what I said before in graph. But in a computational environment, we do the same stuff at the top, then send the index and the command do me a mean to storage. Storage calculates the mean on the first chunk, returns just the mean. Suddenly I'm moving much, much less data. I'm moving 3 numbers instead of God knows how many numbers I've got in each chunk. So that's the how can we do computational storage and why reductions really help us in terms of the data movement. There's a bit more complicated stuff going on here. The storage trunk might have some missing elements. For example, if it's the UK in that storage chunk, then that's fine. But what if I'm interested in the ocean, right? Then clearly the land's going to be missing. So there are all sorts of things about missing, and there are other things to worry about, byte order and stuff like that, and what kind of compression I did. And I'll give you a better example of that in a minute. So let's think about the gory details of doing this. So my application is writing some stuff through a storage client to some kind of object storage service, which is then writing some object storage targets, some sequence of blocks. This is what we're all familiar with going on in some storage system. So that's kind of a single server. This will do fine because every block's coming through here. The OSS can work out how to do this. If you can get the command along there, the OSS knows what to do. Bit more of a problem if everything's going on in the kernel and it's striping the stuff across all of the OSTs, then I'm not going to get any benefit because I have to bring everything back here before I do the computation, in which case I might as well not bother. I'll just do that in my application. So we do need to worry about the guts of what the storage is doing. Okay, so we have a couple of implementations of where we're at. S3, it's easier to talk through S3, so let's just talk through that. So we have some S3 server writing a sequence of objects. S3 server shards the stuff. We don't care too much about that. But when we're reading stuff, we've got a new application sitting in this space called Reductionist. And it does what it says on the tin. The storage client can request a computation. It'll read the chunk, it'll do the computation, returns the result. So it's just an intermediary piece of middleware. Second, it's very easy to see how that will work in S3. And you can even see, and what we do is you post a request for an operation, and there's a handful of parameters, and I don't expect you to read this, and I'm not going to read them through. The point is there's a handful of parameters given to the storage, but the storage does have to do some stuff. It might have to decompress, so the storage has to know what of storage decompression algorithms might be needed. And so there are some requirements on the storage, and the response is pretty simple, right? 42, always. Okay. There is an issue. How do we find the chunk in the file? And that depends on the file format. So this is not file format agnostic. Somewhere the application has to work out where the chunk is and request and tell the storage where the chunk is, what size it is, and all the rest of it. And there are 2 interesting formats for us. HDF is very common, where essentially it's a file system in a box with an index, and ZAR is a set of chunks with an index outside. Both ways we have an index. We can work with that index and tell the storage where all the stuff is and get on with it. Posix. The big question in the Posix environment, it's really easy in S3 to think about how I'm going to ask for an S3 server to do a computation. It's just another HTTP message. But how do we do that with Posix? Harder problem. Oops. Oh yeah. So the solution here is to hack IOCTL, the Posix command, which has very few semantics, and add some extra stuff, so it can send a request to the storage, and the storage can receive the request, do the computation, and come back. So you get, if you like, the command out of band completely from a normal storage thing. So the storage client has to be hacked to do this. And our colleagues in DDN have actually done this. They've done it in a Fuse example to get the proof of concept, and they've done it in their Infinia product to demonstrate that this works. They haven't managed to do all of that complicated API with the missing and all the rest of it, but it's working. It does means and reductions and so on. So we have a fully featured S3 implementation and a proof of concept Posix implementation. But there are some issues, one of which is that file system in a box has got the chunks all over the place. So if I was trying to do this in Lustre, I've got a problem now because I really want to make sure that my chunks are all in the same place so that when I try and do the computation on the chunk, I get a chunk. And so we have a problem in Lustre with HDF. ZAR, it's relatively easy because each chunk's a file, so it's very easy to tell the storage system what to do. On the other hand, every chunk's a file, and so you have another order of magnitude or 2 or 3 orders of magnitude of files, which is a different class of problem. So there are some problems in the Lustre space, but these are not beyond the wit of the people in this room and elsewhere. So I think we can solve this in Lustre. That's the opportunity, if you like. So the compute requirements are quite simple. You need to be able to address a byte range within a file and fill a buffer with them because you need to do some stuff to the buffer. Incidentally, we did think about streaming this, but it's easier to do the proof of concept as a buffer. You need to be able to, you need to know what kind of filters and decompressions, and effectively that's the ones that are left in terms of the requirements you get from ZAR and NetCDF. You need to support some defined operations. What are the reductions we want? The obvious set corresponding to the MPI, your mean, sum, max, min, count. You could imagine that some kind of FFT if you had the right kind of chunks. There could be other things you could do as filters in there. But you'd have to think quite hard about how to turn the algorithm into something that worked on chunks. And there are obvious error messages that need to be handled. But this is all simple. I mean, the actual implementation of this is much, much simpler than the how do I get the command to the storage system. On the client side, as it currently stands, our science applications use a piece of code called CFPython, which is climate forecasting domain analysis, and it uses Dask. And in the current implementation, what we've done is we've hacked CFPython to manipulate the Dask graph. We've also, in a little fork of Dask, hacked the Dask graph directly so that we wouldn't have to use CFPython. So everything here up could be completely oblivious. All it has to know is there is a storage device present for this file which can do active storage. But at the moment we're handling it here because the reason we haven't done a proper pull request into Dask is if I was the Dask maintainers, I wouldn't be taking a pull request from this until there was some storage in the field that people could use. So we're doing it up here so that we can build something we can build something and demonstrate it, get it working, do some science, and then there's more incentive for storage people to build things, and then there's more incentive for the middleware to completely hide this in just the same way as MPI libraries hide it. And so further down the stack, we then have this thing called PyActive Storage, which does the heavy lifting. It's the bit that knows if the file is able to do, if the storage device can do computations, and if it can, it will hand off the request to do a mean or whatever and get the result. If it can't, it'll just hand off the normal request, receive the results, and do the computation itself. So it's just a little shimmy in there, that no different from what would have happened in Dask itself. And indeed, the fix for this for Dask is simply to replace the Dask functions which do things like mean with our own ones. So it's, as I say, it's quite simple. So I've just said all that. It could be done in Dask. We've done it in CFPython because that's where we're at in terms of demonstrating this. So I'm pretty much at the end. So we've built and tested some code that does push into the storage the ability to do filters. So the filters that we need to do are things like byte shuffling so that the compression works well. And then the compression itself, the decompression is what we need to get back. Because currently, of course, what we do is we filter and compress and send the compressed bytes to storage. But in the active storage, we don't want the compressed bytes back. We want the result back. So we have to hand the storage the information to do that. The S3 implementation to do this is feature complete. And we're going to do performance testing next year. The Posix implementation in DDN Infinia shows promise. As in, it works, it just isn't feature complete yet. And as I said already, the existing version is domain specific for us, but we know how to make it properly cross-cutting, which is one of our objectives. And so the last thing I wanted to say was bring it back to Lustre and just say, this is all eminently doable in Lustre, though we have some problems to resolve. One is, how do we get the chunks aligned on the OSS so that when you send the request, the OSS has all the data that it needs to do the computation. Then there's an interesting question about how that interplays with striping. And then what do we need to do to put the computational facilities in there? Essentially, three problems. One is the control. Do we really want to use this overload of IOCTL method that I was talking about before? That's essentially JT Acquaviva at DDN's smart idea, but he's also smart enough to say there might be a better idea, and he'd be quite keen to hear it. Software, we need to put all the pieces in there to do the actual implementation, so that means pushing in some of these filters and decompressions. And finally, the hardware, just to make sure we believe we can hold the buffer for the chunks to do this. But these are really small tasks for proper storage vendors. So I'll leave it there.